So, like I said, these local functions, they are solutions to an atomic problem represented on radial logarithmic grids, and there's a pseudization procedure to compute out of these all-electron partial waves, pseudized partial waves, and a pseudized local potential. And then there's procedures to construct these projector functions. And the only real requirement is that they're dual to the pseudized partial waves. And in this, in these quantities, we can rewrite our Cohen-Shum equation in such a way. So so that is the, that is the counterpart to this particular equation, the all electron atomic problem. In terms of these pseudized quantities, one can write this particular equation, where we have, so now you see these projectors popping up. The solutions to this equation are now not the all-electron partial waves, but the pseudized partial waves. And we see a few additional quantities emerging, and those are these Dij matrices and Qij, and those are the so-called PAW strength parameters and augmentation charges. So the augmentation charges, they account for the fact that the norm that is carried by these pseudized partial waves is not necessarily equal to the norm of the all-electron partial waves, and these strength parameters are these particular expectation values of the difference between these expectation values in the all-electron partial wave basis and in the pseudo partial wave basis. And this particular equation yields the same eigenvalue spectrum as the all-electron problem. Yeah? So, and in terms of electronic scattering, one usually represents that in the following way. So these equations should have an identical eigenvalue spectrum. And in scattering theory, we then look at what is called the logarithmic derivative. Those are these quantities. And they should be essentially the same over a whole range of these energies. And then we have a good then we have generated a good pseudo potential. So this is well, not a very modern pseudo potential theory. And there we see the solid lines. They represent the logarithmic derivatives for the all-electron problem, and the dotted lines are the logarithmic derivatives for the pseudized version of that particular equation for this pseudopotential method, the Trouillet-Martens pseudopotentials. And we see large deviations when we move away from the valence part of the eigenenergy spectrum. Whereas the PAW represents these scattering properties over a much larger energy range. And that is normally indicative for transferability. Because with these Trouillet-Martens pseudopotentials, you will be able to represent the atomic problem almost exactly. It will have the same eigenvalues in the pseudopotential description and as in the all-electron one. But as soon as you put that into a chemical environment, the fact that you do not represent scattering properties as truly will start to show up. And the PAW method, because of the fact that scattering properties are reproduced over such a large energy range, will help in terms of transferability. Yes. So what do these functions look like, for instance, the PAW method? So we include for each valence channel, we include two functions in the standard potentials, where we choose one of the eigenenergies at the bound state of the atomic valence, and then one of them at the non-bound state. So that means that we have additional degrees of freedom in our local basis. So the use of the frozen core approximation is also at the level of this PAW, right? So there's a whole bunch of electrons that are only present implicitly by their core charge density. So that is added to all terms, to the exchange correlation terms and the Hartree term as well. Yes. So, and this is maybe a point that is nice to make. We had it in this conversation at the coffee break. It already came up. So in the PAW method, in terms of our local functions, we can express the charge density in such a way. Inside of the PAW spheres, we can do the same in terms of the pseudodized partial waves. And those particular densities are then used to represent the local potential on these radial grids. And that is where, for instance, the PAW method differs from ultrasoft pseudopotentials, because ultrasoft pseudopotentials in computing, we compute these strength parameters. In ultrasoft pseudopotential method, you would use the atomic density for these two terms. In the PAW method, you use the actual density, decomposed in these partial waves inside of these strength parameters. So there's one, and that is from a computational point of view, it's not a huge effort, but it's an additional effort that we have to update these potentials and these strength parameters in every step where the density changed that you would not do in an ultrasoft pseudopotential. Yes. So 3 contributions, like we said. One, plane waves, so that lives in the whole cell, right? These plane waves extend over the whole simulation box. Then there's a part that we subtract that inside of the PAW spheres in terms of these pseudodized partial waves, and a part that we add to it in terms of these all-electron partial waves inside of these PAW spheres. And how much of those things are admixed to our plane wave solution is given by this particular projection. And this particular decomposition of the wave function in 3 parts, in a pseudo plane wave part, a pseudodized radial part, and an all-electron radial part, this sort of carries over to all the quantities that we will compute. So not only orbitals, but also densities and energies will decompose in these kind of contributions. And that is written here for the kinetic energy, for instance. So this is an expression that we already saw before. And now we substitute our, for the all-electron wave function, we substitute our PAW approximation. And there we assume then completeness in these local bases. And that is always only approximately given. But for this decomposition, we assume this to be complete. And then we end up, for this kinetic energy, we'll end up with 3 contributions, of which one is purely plane wave nature, one involves only these partial waves, these pseudodized partial waves, and one contribution involves only these all-electron partial waves. And this is a very essential thing, because if this wouldn't separate in these 3 contributions, if at any point I would have here, for instance, a plane wave object, and here one radial function, then the method would be gone. Because that would mean that to evaluate such an element, where one side lives on the plane wave grid and one side lives on radial grids, I would have to bring them onto a common grid. And then I'm dead, because that would either mean that I would have to take all these fine features that are easily representable on a radial grid and put them on a plane wave grid, prohibitively expensive, not possible, or I would have to throw away everything that lives on the radial grid, and then the sort of the child is gone with the bathwater, right? So this whole PAW method lives from the fact that all contributions can be separated in 3 terms, where there's never any admixture of something that lives on the plane wave grid and something that lives on the radial grids. The only connection, and that is here given by these what is called one-center occupancies, the only connection between the 2 grids is the projection of this plane wave function onto these projection operators. And there we have so much choice of freedom in these projection operators, because they only have to be dual to these to these guys, that we can choose them of a form that is easily representable in plane waves. So that is why the PAW method actually works. So actually this is a bit more general. Any semi-local operator can be shown to be written in this form. So if you have a semi-local operator A that acts on the true orbital, the PAW method, through the constructions that I showed you before and through this assumption of completeness, the PAW method associates a pseudo-operator of this particular shape that acts on these pseudodized orbitals on the plane wave part that acts on the plane wave part of the PAW wave function. So this expectation value and this one are exactly the same. And the plane wave part of this all electron wave function is actually the variational part. So that's the part that our computation tries to compute, right? That VASP tries to compute. Because you see these guys, these ones, and the projectors, they are given, they're computed, pre-computed and specified on the PODCAR file. The only thing that remains to be determined is this plane wave part. So that's the variational part. So that is here. There's another example of this for the density operator. You see that it separates again into 3 of these terms. A plane wave part of the density, a part expressed in pseudodized partial waves, and one expressed in all electron partial waves, where the last two live only inside of these PAW grids in the PAW spheres on logarithmic radial grids. So non-local operators are a bit more complicated, and I won't go into the details. The thing is that what is done there, there's an additional trick employed there so that we can separate expectation value of a non-local operator again into these 3 parts. Because what is non-local in the first non-local thing that we have is already the Hartree potential, right? Because it doesn't depend only on the position, but it depends on R and R prime. So in that sense, it's non-local. And what is done there to achieve again this separation in 3 terms is that on the plane wave grid, inside of the PAW spheres, there are soft compensation charges added inside of these spheres, and these soft charges, they restore all the correct moments of the charge density inside of the sphere. So not only the norm, but also the first and the second moment and what have you not is restored, so that the potential that is cast outside of this sphere by the density inside the sphere is the correct one. Because if you have the moments inside of a sphere correct, then the potential outside will be the true one. Yeah, so that is done. And these soft compensation charges, why is it soft? Well, soft in the sense that they have to be representable in terms of plane waves. Yeah. So that means that the potential in the interstitial is correct by adding these charges. And then the fact that we have messed with this charge density is then compensated by the fact that we add these compensation charges on the radial grids as well, where they are subtracted out, right? So we have the long-range interactions between charge density is corrected on the plane wave grid, and the fact that we have messed with this pseudodized charge density is corrected on one of the radial grids. And then again, for instance, in the Hartree energy, this means that we again separate the energy contributions into a part that is evaluated completely on the plane wave grid and 2 parts that are evaluated on the radial grids. So in that sense, you can, for non-local operators with these tricks, with compensation charges, you can make sure that you can that again, we can decompose it in these three contributions where there's no crosstalk between plane wave grids, between the regular grid and the radial grids. Yeah. So in that sense, our total energy actually decomposes into three contributions. So we saw that for the local operators and for the non-local operators. And so in total, we have a part of our total energy on the plane wave grid and two parts stemming from the radial grids inside of our PAW spheres. Right. So, and here, well, this is a point that I've already made a few times. So what is good? What is good is that we, and that is what you saw. So the strength of the PAW method is lies in the fact that we have, well, that we represent the scattering properties of the atomic problem over a wide range, so they're highly transferable. Another strength is that that due to the fact that we have these local functions, the atomic ones, and that we make this reconstruction of the nodal features, so we implicitly work with the complete all electron function, means that we remain orthogonal to the core. So many other pseudo-potential methods suffer from the fact that you have a certain amount of non-orthogonality to the frozen core states. That is not happening in the PAW method. So that's two things. High transferability and orthogonality between core and valence state is sort of guaranteed. Yeah. So, and the essence is that we never put quantities on one common grid. So we never try to put radial functions onto the plane wave grid or vice versa. Otherwise the methods would immediately break down. We get a lot of questions because, and I can understand this, people would like to visualize the wave function, say, but can I not visualize the PAW wave function? And I say, no, actually you cannot. Because of the fact that the PAW method works, you cannot visualize the wave function. Because to visualize it would mean to bring everything on a common grid. I would like to reconstruct this wave function. That's never explicitly done. So this what we saw here, this object is never explicitly calculated. If there would be a need to do that, then the whole method, you could throw it away. Then you could work with the common grid immediately. Yeah. So, okay. So the pseudo-orbitals are the variational quantities. These plane wave pseudo parts, those are the variational quantities. This is just a recast of the previous equation, where now, by the way, you see here, before here we had these pseudized partial waves, but actually, obviously, in real life, we're not trying to represent those particular ones, but we want to compute the plane wave part of our PAW wave function. So that's the actual equation. The charge density used in these strength parameters is the actual one, so not the atomic one. In that sense, it's different from ultrasoft pseudopotential theory, and those are the representations of these charge densities inside of the spheres. So is it accurate? Yes, it is very accurate. So this is a recent publication where a lot of work has been put in comparing the accuracy of PAW potential sets with all electron calculations, sort of benchmark them. And yeah, if you're interested, there it is by Kurt Lejagere, and it's published in Science some time ago. And essentially what they compute is a measure. So this is the volume versus energy curves of one code, let's say our code or any other PAW code, and an all-electron code, and the area where they're different is computed in terms of energy, and this is the measure of the average deviation you would find for elemental elemental solids of all these elements, and that is truly, truly tiny. Actually, for a long time, the hardest part was for the all-electron methods to agree on a common value and not for the PAW codes. So that was a nice detail.
What are the numbers inside the box?
So they are the individual contributions to this average value. So for instance, for boron, the delta, so this area in the difference between these two curves is 0.2 milli-electron volt if you compare the calculation. Yes. Yeah, yes, well, Europeans like to use commas sometimes. Okay. It means the same thing. Yes, no, I got this picture from Kurt, and he for some reason, I think it's standard in some programs. It's standard. If you use Open Office or Microsoft Office in the European version, you would have to go through I don't know how many menus to find a point where you can change this actually. Yes. Yeah. No, this is 0.2. Yeah. So this is a comparison against, already spoke about this before, against the Gaussian basis set calculations. So this GTOs, Gaussian loop orbitals. Yeah. Anyway, for the G2 test set, so it's a set of small molecules, and this is done. This was actually work where we are benchmarking our hybrid functional code. So this is for PBE and for PBE 0. It's the difference between Gaussian calculation and a PAW calculation, and it's in almost all cases it's smaller than 1 kcal per mole. The energy differences of these atomization energies of these small molecules. And 1 kcal per mole, that's something that will pop up at several occasions. That is what is commonly called chemical accuracy. So any method that reaches this is the winner. And of course, with respect to experiment, right? Because that is sort of the accuracy that they can reach in experiment, and that would mean if your method guarantees this, you wouldn't need to do the experiment anymore. This is, of course, agreement of two DFT calculations, right? So this is not close to experiment, but they agree amongst each other at least. So let's, yes, let's do this. Electronic minimization. So we have spoken about the fact that, so here, unfortunately, I think I've left out the fact that we work on pseudo-orbitals. So let's forget PAW formalism for a while, right? So these are the orbitals that we want to determine, and we said, okay, so we have to solve these Cohen-Shum equations, and there's essentially two ways that that one can do this. So one is direct minimization. So we could start with a set of trial orbitals and minimize the total energy by following the gradient on the orbitals in the direction of decreasing total energy. And the gradient on the orbitals is actually something like this. Yeah, so this is the action of the Hamiltonian on the current orbital minus its current approximate eigenvalue. This is what you called the gradient. It's sometimes also called the residual. We saw this before. Yeah. So and admixing parts of this to the current orbitals means that you can use conjugate gradient or any direct minimization method to follow this to to a local minimum in the total energy. So that is, for instance, done in Carparinello. The thing that we commonly do is called the self-consistency cycle, and that's slightly different. We don't start per se with the trial orbitals, but you can start with the trial density, and then you construct the Hamiltonian in accordance with this density, and then, essentially diagonalize it, so solve this particular equation, and that will give you a new set of orbitals and a new density, and then you mix this new density with the old one, and that defines a new Hamiltonian that you again diagonalize. And so that is different. Here you work directly on the orbitals. Here we do a diagonalization and work with the density. And that's the self-consistency cycle. And that is actually, well, that was shown to be a bit more efficient than the direct optimization, especially if you go to metallic systems. So and that's a comparison that is shown here. So here we have convergence in the total energy in the self-consistency cycle, and here we have it for several different system sizes at a sort of longish disordered diamond cells. For different sizes, we have that here in the direct method. If you then go to a metallic system, you see that that self-consistency cycle still manages to converge in a reasonable number of iterations. But if this becomes larger, this cell in a certain direction, then this direct minimization will have huge troubles finding the ground state. So we tend to rely on this self-consistency cycle and charge density mixing. The problem with this situation, especially with this situation in the direct method, is called charge sloshing, and that is something that I've tried to explain here. So the gradient we can decompose in two parts. The gradient we saw before, we can compose it in a part, in the gradient part that lives in the subspace that is spanned by our current orbitals. That is this part, so which is often called the subspace rotational part. And there's a part of the gradient that points outside of the space that is spanned by our current orbitals. And that is this part. And it's actually this part where of the gradient that lives inside of the subspace that is spanned by the orbitals that poses the problem in direct minimization. And that is because of, well, what you see here. This is a Hamiltonian, a matrix element between two states that we currently have. And this is their occupation. So this part exists only if parts of our states are so only between parts of the spectrum of unoccupied states and occupied states, right? So it's a rotation between an admixture of unoccupied to occupied states. That is part of the gradient. So considering two states very close together, and that is what you would have in a metal or in a small gap system. If you have two states that are very close together, then a small subspace rotation will admix, well, parts of one to the other, and vice versa. And if you look at what that means for the change in the density, so we suppose that these states are essentially plane wave-like, then they're representable in this way. If we then look at what that means for a small gradient, that means that we have a gradient is of this form, and the change of the potential due to this is inversely proportional to the square of this small difference that we have in our wave vector. So as we have a small difference between this one and this one, the admixture of these states with each other yields a huge response in the potential, in the electrostatic part of the potential. That is something that often pops up. We try to counter this with clever mixing of the charge densities. That is why sometimes your systems will not converge, because you have this charge lossing. Very small, long wavelength changes in your charge density yield huge responses in your potential, and your iterations will become unstable. Because the largest stable step that you could take would be connected to the so this change in the wave vector is connected to the size of the cell. That is why the small, so this is like a particle in the box, and it's connected to the inverse of the length in your cell. So if you have, for instance, and maybe you have noticed this, if you have a system that is long in one direction, it's harder to converge it than if it would not be. And that's because of these effects. So if you have a surface that is long in a certain direction, because you have this vacuum, this would possibly immediately pop up. Yes, so the smallest stable step size that you would have here would be inversely proportional to the square of the longest size of your cell in terms of charge sloshing. If you have a large gap, that doesn't hurt you so much, because then this will be very, very small. But smaller gap systems will be strongly affected by this. So what we do to counter this, or what in the self-consistency cycle counters this, is the fact that we set up a Hamiltonian for a certain density, and we compute these wave functions. Well, I've written here iterative refinement of the wave functions. I'll come back to this. But essentially, we do a diagonalization, and that yields us wave functions that yield a new charge density. If I would use this new charge density in its totality, then charge sloshing might kick in immediately. But that we don't do. Instead, one admixes it only partly to the previous charge density, and it should dampen out these effects of charge sloshing. So a clever mixer will be able to dampen out these effects. This mixing will give a new charge density, and this whole thing is taken for another spin. So, so two things that are important. One is iterative diagonalization, because we said before we diagonalize this Hamiltonian, but we don't want to diagonalize it exactly. Come back to this, but we do this iteratively. And another thing, another key point, is density mixing to keep effects like charge sloshing under control. Yes?
When you start the self-consistency cycle, we have to give a trial density chart.
That
How do we give that, like the trial first one, right in the middle?
The first one is commonly constructed from the atomic charges. So the atomic charge density is also information that is carried on the PODCAR file. And the program will take all the atomic positions and put atomic charge densities on the respective positions, and that will be your initial charge density. So that is the standard behavior. You don't have to do anything for that. And that is quite a good common choice. If you then look at what happens in the program, so if you start from scratch, if you don't have wave functions from a previous calculation that you can use to restart, then it will start from atomic charge densities. And there will be a few steps where the charge density is kept fixed. So depending on the algorithm you use, the first few steps, the charge density, the first 5 or 10 steps, the charge density is kept fixed, because the wave functions that you use, they are initialized with random numbers. So they might be pretty bad, because we do this iterative refinement of the wave function. So we do not exactly diagonalize the Hamiltonian, only on its way the wave functions are improved. But starting from random numbers, the charge density you would get out of this first step would be really, really bad. So you don't want to mix that to something that is pretty reasonable, because atomic charges are pretty reasonable. So for the first 5 or 10 steps, the charge density is kept fixed at the atomic one. Wave functions are optimized a few times, and then the mixing kicks in. Yes. So why do we not do a direct diagonalization of the Hamiltonian, an exact one? Because you could envision that doing that, you set up a Hamiltonian, express it in plane waves, and simply diagonalize it, and you end up with a bunch of eigenstates and eigenenergies. So this would be a matrix of the size of the number of plane waves in our FFT grid times the number of plane waves in our FFT grid, and you diagonalize it. There's software to do this, or libraries, but you end up with n FFT eigenfunctions of your system, and you don't need so many, because this For instance, imagine the worst possible situation. That would be a small molecule in a large box. So NFFT might be 50,000, for instance. But for this small molecule, you need only 4 states to put the electrons in. You only want to occupy a few states. You're not interested in 50,000 eigenstates of this system. You only want 4 of them. Yeah, so, and diagonalization commonly scales cubically with system size. So you pay a heavy price for an exact diagonalization of this matrix, and you have to store it. So you don't want to do this. And iterative diagonalization is a way around it. You can, by means of iterative diagonalization techniques like Bloch-Davidson or RMM, you can iteratively determine the 10 lowest eigenstates of your matrix, and not all of them, right? So that is why we don't actually do the exact diagonalization. Okay, so yes, so that is the reason that we use all these nice methods like RMM Dias or Bloch-Davidson. Yeah, so another key ingredient is subspace diagonalization, and that's one of the things that we have spoken about before. So the subspace is the space spanned by our current orbitals. So, and essentially the things that we do in iterative matrix diagonalization methods is Rayleigh-Ritz diagonalization and in this iterative subspace. Yeah, and that is only of the size of the number of bands that we want to compute. So let's say of the order of the number of electrons in our unit cell times the number of bands. Yeah, so these are small diagonalization problems, much different in that sense from this one, which would be a huge one, right? So iterative matrix diagonalization depends on Rayleigh-Ritz diagonalization in the subspace of the current orbitals, where we have our Hamiltonian in this subspace, and in our case an overlap operator, and these approximate eigenenergies, right, which are the diagonal entries of this matrix that is being diagonalized. Yeah. Another key quantity is the residual, that essentially tells us how far away from exact our eigenfunctions and eigenenergies are, right? Because for an exact state, obviously the residual would be 0. H psi is then H psi is equal to epsilon psi for an exact eigenstate. Yeah. So yes, this is sometimes a bit complicated, but I want to give you a taste for what happens and mention some of the buzzwords connected to it. So yes. Or do you, oh, sorry. Yeah, so Bloch-Davidson, what would you do in a Bloch-Davidson algorithm, which is one of these iterative diagonalization methods by which we compute the so-and-so many lowest eigenstates of our eigenspectrum of the Hamiltonian. So what you would do is you would take a subset of bands in Bloch-Davidson, so this is the block size, and you extend this particular subset by a preconditioned residual. So the residual, that was this H minus epsilon working on these orbitals, and then it gets preconditioned. We can quickly forget this, but essentially this gives us the gradient on our orbitals. So we construct a subspace of our current orbitals and the gradient on them, and then do a diagonalization, a Rayleigh-Ritz diagonalization in this particular subspace. And that gives us well, eigenfunctions in this subspace, and then we apply again the Hamiltonian on these eigenfunctions. That gives us another extension of our subspace, so it grows a bit, but it's only like, for instance, you would commonly take 4 bands and then construct, then compute the gradient, and you have a subspace of the size 8, and then you might diagonalize it and then compute the gradient again on those orbitals. Then you're at size 12. And so the basis in which we do this diagonalization is growing, but it's very, very small. So it's not a really a big problem. So after a few of those steps, where the space is growing, and those spaces are commonly called Krylov spaces. So I don't know if you ever come across this. This is a Krylov method. So as your search space is continuously, as you add h psi to your search space, you come closer to these eigenfunctions. So after a few steps, and commonly we don't do more than 3 or 4, you take this optimized set and replace this bunch of bands that you were optimizing with this set. Then you move on to the next block, and at the end, in essence, the only thing that remains to do in the end is an orthogonalization of all these functions with respect to each other. So that is how Bloch-Davidson would work, and how you would approach with each of this. As you are increasing your Krylov space, the diagonalization that you do comes closer to the exact eigenfunction of one end of the spectrum. Depending on how you set this up, you can get the lowest eigenvalues of your eigenspectrum or the highest ones. But we obviously use it to get at the lowest so many eigenfunctions and eigenenergies of our Hamiltonian. And that is obviously still, the Hamiltonian here is still at constant density. So you do a few steps of this iterative refinement, and then an orthogonalization, and then you compute a new density and mix that one, and then it goes back into this guy. So that is essentially how the self-consistency cycle works. So, and in the density there we said, okay, we don't want to use the complete new density, because then the whole thing will become unstable. And I don't want to really go too much into this, but what is essentially done in programs like VASP, and other programs use this as well. They use Broyden mixing, and Broyden mixing constructs a model for the dielectric function. So the dielectric function tells you how strongly will my potential change if I change my density a bit. So knowing this would obviously help you to dampen out huge variations, right, that you wouldn't want. Of course, as soon as you have computed your ground state, you could compute the dielectric function and you would know it, but you wouldn't know it beforehand. So Broyden mixers will start with an approximation to the dielectric function, and that is well, these parameters that one can set for the mixing. They use an approximation for the dielectric function, and with every step, the mixer learns something about this response and start to refine this model. So as you are mixing, it becomes more clever at mixing and getting rid of huge responses. At some point, the mixer it stores information for this, and that is expensive to carry around indefinitely. So at some point, the mixer will get reset, and that is why you might sometimes see that all of a sudden your convergence behavior worsens again, because then the mixer gets reset. Yes. Anyway, that is in a nutshell what the Broyden mixer will try to do, and these parameters that sort of give you the shape of your dielectric function, there's defaults for them, but they would not work equally well always. I mean, the defaults are chosen such that it works well in many cases, but that is one of the things that you might want to try to play with when you see that your system is not converging as rapidly as you would like. Yeah, or not converging at all, mostly. Well, where does this pose a problem? There's, for instance, in magnetic systems, we often see this. The mixer is learning about the response of your system, but the first part of the strongest response of your system is the electrostatic response. So it's constructing a mixing function that is very good at predicting which new charge density to choose with respect to electrostatic interactions. but the relaxational modes of the magnetic system, they are of a completely different order of magnitude in the total energy. So this function that gets constructed will not be very effective at mixing the magnetization density. So if you do magnetic systems, it might help to do like 20 steps of self-consistency and then stop the calculation after 20 steps and restart it. You will restart with a fresh mixer that will be much, for that particular mixer, the magnetic modes will be much more visible at the beginning, because the responses at that point will be more strongly dominated by magnetic modes, for instance. So it's some of those things. Yes, and then there's horrible systems that will simply refuse to converge. Yeah, one has to play with it. Good. That was the end of this particular talk. Any questions before? Let's do a few questions, if any, before we break. Right? Yes.
So you show the difference between the direct minimization and there's a self-consistent minimization approach, right? And then you show there saying disorder diamond timer and disorder FCC. So I'm a little bit confused. What do you mean that disorder? Because they are all pure.
Slightly perturbed. So I mean, I don't in this. So there are longish cells, and you see here that you see there's sort of the atomic positions have been slightly perturbed.
And then in this case, you're trying to get one ionic relaxation. This process.
This exactly, well, so the positions are kept like fixed, yeah. And this is the electronic convergence. Yeah. Yes.
So in one slide you have a table of comparison of the PW method with the all-electron method.
Mm-hmm.
There are some elemental materials that PW doesn't have a good job. Something like that LU, the third column. Last line of a 3.5 milli discrepancy.
Ah, yes.
Some
so lutetium.
And,
yes. Yeah, lutetium is.
Comments on why for certain elements it doesn't do a good job?
Yes, and that is so that is where the actinides start, right? No, sorry, the lanthanides. Lutetium. Okay. Yes. So they're notoriously difficult, but even worse, there's only well, not the most effort went into creating those pseudo-potentials. So because they're not so commonly used, so there's like these PAW data sets, they have grown organically. So the ones that are used very, very often are of the highest quality in most cases. So I guess that this was an old calculation actually by Kurt, because normally Georg, when he sees numbers like this, he starts to work on the potential. One should, as a side issue, one should be aware of the fact that this delta value, so it looks like most of them are very small, but a delta value of 2 is already almost perfect agreement. So 3.5 is definitely something where you might look, but it's not a red light. Yeah. So, of course, in these kind of studies, it then becomes sort of the game that everybody tries to approach 0 as best as possible. But I mean, everything from 2 and below is almost perfect agreement. So, yes. Yeah? Oh, sorry.
Have there been studies that compare the experimental determined charge densities with VASP charge densities? Can you comment on that a little bit?
There are people that do this, obviously, with crystallographics, and they would use mostly Bader analysis and then compare spectra that come out of this. So they decompose the Bader charges on the atoms and compare this to diffractional experiments that I know of. Yes, so
Yeah.
I don't know how well this is how well that compares, but
Judging by the table, it seems like they should compare well.
yeah, but the thing is that this is DFT against DFT, right? And as soon as you say experiment, then things change. I mean, this should essentially, here you would expect, if everybody does their job, this should be 0, sort of, right? And DFT compared to experiment or hybrid functional or what have you not, there will always be a difference. Yes, so there it would not necessarily mean that something is bad. It's simply that your approximation is limited, right? Yeah.
So we have a number of questions from online participants, including a few from this morning's session. I'll start with the more recent questions.
Mm-hmm.
In the case of a crystal, why do you only need the lowest 10 eigenfunctions?
In the case of a, well, 10 was just, 10 was, so in the case of a crystal, why do I only need the 10 lowest eigenfunctions? Well, 10 was just some number that I came up with. I mean, you don't need 10 eigenfunctions always, but what you need is you need enough. Sorry, why don't I find this now? Yes, so what we need is we need enough functions to be able to represent the density, right? Yeah. So the density is constructed. Well, here it's a sum over this n, the number of bands, and in each of these 1 electron orbitals, we can put either 1 electron or 2, depending on whether we consider spin polarization or not. Yeah. So let's forget about spin polarization. Then for each of these orbitals, in each of these orbitals, we can put 2 electrons. So if I have a unit cell which contains 50 electrons, I would need 25 orbitals to be able to put them in, and then I can compute the density. So in that sense, we only need a limited number of the lowest eigenstates. Because if we look at our total energy expressions, we see that they I don't know if I have that one, but essentially you can compute the total energy as a sum over well, it's not this expression, sorry, but you can represent the total energy as a sum over the eigenenergies. So you would, if you would fill your states with electrons, you would fill the lowest ones first, because that would end up with the lowest total energy, right? So yes, so in that sense, we only need a limited one, and we need a limited number of the lowest eigenstates of our Hamiltonian. Yeah.
Okay, so another one. How are different how do the different versions of the same PAW, either LDA or PBE or GW, or different types of LDA and PBE, how are the different versions of the pseudo-potentials different?
Right.
Case by case, how transferable are different types of pseudo-potentials for specific types of calculations?
Right. So that is a very good question. That gets asked. So actually, it gets asked so often that we should probably make it more prominent in the manual. Yes, the transferability of the potentials would actually mean that it's not so important that you use a potential that is constructed with the functional that you are actually going to use. The transferability of the thing should be enough that should not really matter. So I should be able to do an LDA calculation with a PBE potential And that is exactly what happens, or do a hybrid functional calculation with a PBE potential, because we do not generate potentials that are used in hybrid functionals with hybrid functionals, right? So we can, so there you are forced actually to use either an LDA or a PBE, and it should not matter a lot. The potential should be transferable enough that it should be able to deal with this. So the fact that we have different versions is sort of a historical thing, and it's limited to the fact that we can generate these potentials only for LDA and for PBE, and I think for revised PBE, something that does not get done anymore even. So we do still generate them for LDA and for PBE. For a long time we were doing GW calculations with LDA potentials because they were only generated for LDA. Now that has been taken care of, you can use PBE ones there. I standardly use PBE potentials unless I do an actual LDA calculation. There I might use the one that has been generated with LDA because I have it, not because I think it is so important. But since I have it, I would use it. The difference between, then there's differences between the potentials, and so not related per se to the functional with which they were generated. So there's always these, well not always, but there's versions that are called _H that are harder ones. Those generally have a smaller core radius. So if you have, for instance, some bonding situations with extremely short bonds, then it might be that you would need a harder potential with a smaller pseudo-potential core, so that those cores do not overlap so strongly. So typical situations are oxygen dimer, for instance. So there's an O potential and an oxygen _H potential. So if you're in some situation where you have very short bonds between nitrogen and oxygen or what have you not, you would need to use a harder potential with a smaller core. Harder because as soon as the core becomes smaller, you would, due to all kinds of reasons, need more plane waves to represent the resulting pseudo wave function.
So you may have just addressed one of the other questions, which is what's the difference between a hard pseudo-potential and a normal pseudo-potential?
Yes, it is mostly the size of the core. The GW potentials, and that will come up in another talk, they are a bit different. The size of the one center basis has been increased. So we have looked at, and I will make this point again, but we can quickly go to it now. Sorry, where is it? Yes, so I've mentioned this before, that we represent the scattering properties of the atom over a certain range of energies. Normally it is sufficient that this range of energies spans energies that are close to the bound states of the valence. Of course, the eigenenergies in a chemical bonded situation will be different, but if it's over a range close to the valence, it's enough. For these methods that are now becoming en vogue, like GW, where we need part of the unoccupied spectrum, you would need to represent the scattering properties also high up away from the occupied states. And there is potentials where there has been extra taken care of the fact that scattering properties are truly represented up to a much higher energy within the spectrum, and those are those _GW potentials. They're slightly more expensive because the one center basis is larger, maybe slightly harder, but not necessarily so. So you could use them for ground state calculations as well. So, but if you are interested in lots of unoccupied states for whatever reason, then those are the kind of potentials one should use.
So a couple more questions around pseudo-potentials.
Yep.
How would you go about visualizing or plotting the pseudo-potential itself?
Yeah, the okay. So common quantities that one would plot in connection with pseudo-potentials or their generation would be such a thing, but I take it that that is not necessarily what is meant here. But yes, so we have all kinds of horrible scripts that do this. but yeah.
And somebody else asks, what does a pseudo-potential for hydrogen mean, since there are no core electrons in H?
A core.
Just a core.
Yeah. Yes. Yes, something other than a 1/r core, obviously.
So we have several more questions online that might throw to the room.
Yep.
Can you stand up to us?
In the diagonalization, do you use also symmetry adaptation of the bases in order
No. The only, so in the diagonalization, where does symmetry enter there? The symmetry enters due to the fact that we have reduced the set of Bloch wave vectors by symmetry. So symmetry enters, of course, in setting up the Hamiltonian, because we must symmetrize our charge density before we construct the Hamiltonian out of it. And then the number of Bloch wave vectors for which we have to solve this is reduced by symmetry. Because this problem essentially, so that is not necessarily expressed very clearly on the slides, unfortunately. But if we do the action of the Hamiltonian on a wave function, or compute its expectation value, the Bloch wave vector of this entity and the one we use on the other side is the same. It is diagonal in reciprocal space, right? So they only couple through the density, unless you use hybrid functions where things are different. But you compute the total density. There's a sum over the k vectors, but then in essence, computing Hamiltonian elements is diagonal in reciprocal space. So the effort scales linearly with the number of k points that I have in my reciprocal space sampling.
But so for each k block, say k point block, there is no symmetry adaptation?
No, because in essence plane waves well, you could construct stars out of them, but there's no real need to do that here. Yeah, it is done obviously in the step where we symmetrize the charge density, because symmetrization of the charge density is done in reciprocal space, and there you would construct these stars out of them. Yeah. Mm-hmm.
You showed some comparisons with Gaussian codes. How do you make sure that the basis sets are comparable? Is that infinite basis set limit or?
Yes.
Oh, okay.
Actually, in this comparison, I don't know. I have another one. I mean, yes, but in essence, that is done, or we simply crank up the basis set as much as possible, which for the small molecules is still possible, right? There you would not have to extrapolate per se, but yes. So that we have done this, for instance, and that was a nice one for a chlorine dimer, and then it turns out that well, it's on one of the other slides that you will get to see. That you have to go to a huge basis set and use a sufficient number of plane waves on the same time, and then you see that the results agree, but only if you crank up both methods completely. Is it so important? I mean, yeah, if you want to go to agreement of 1 kcal per mole, it is important. For many situations, it would probably not be so important, and you would use a smaller basis set for, I don't know, I don't know Gaussian well enough to be able to say for this you should use that, or for this, but I think that is pretty well known and pretty well characterized, especially because this G21 test set was obviously chosen because it's one of the Popel's sets, right?
A vector potentials, how do you decide which potential to use?
We have a recommendation on the website in the manual. So I would start with the recommended ones. If then, for instance, yes, for GW I would use the recommended GW one. And then there's nothing that one can, there's no guarantees. Let's put it like this, right? So if you have the feeling that maybe that it would maybe pay off for this particular compound that you're studying, it would pay off to include more electrons in the valence. You might look whether there's a potential that includes a part of the core into the valence. There's all kinds of these varieties, because any recommendation is only a general one, and the particulars of where people use it we cannot predict beforehand. So one always has to test.
And
yeah.
This might be a related question. How does one treat rare earth systems that have open 4F shells?
Yes, that is. So if you're lucky, then if you're lucky, then you can put the 4Fs in the core. So if they're strongly localized and they do not contribute to the binding, then there's varieties of potentials that are sort of ionic potentials. You put the 4Fs into the core, and that would be very good, for instance, for 3+ rare earths in ionic systems or something like that. As soon as 4F, as soon as the F electrons start to build bands, or if you have metallic states, and then you would have to include them in the valence, and hope for the best. I mean, the problem is that those electrons they're often strongly localized, and then it's not so much a problem of the PAW method. Actually, the PAW method can deal with this, but it's DFT. So DFT is not good for these strongly localized states. It wants to delocalize them too strongly, density functional theory, or most density functionals. Let's put it more specifically, and then it might end up that your calculation has not a lot to do with the physics, with the physical reality, right? So yes, they're notoriously problematic systems.
So are there any utility codes available to kind of convert between the PAW and EPF format, VASP, universal potential format?
No.
Because Ebony or PWSCF, they offer the
I know.
format. So
Yeah. I know that yes. I was present at the workshop where they discussed this. Interest from our side to do this is limited by the fact that we sell our stuff, and so yes, is that a good thing? I don't know. It's good for us in the sense that it allows us to maintain the code. Would it be nice to use other potentials? I don't think there's a real need. I mean, this study has shown that that there's a few good sets of potentials out there that one can use, and we are among them. So I don't know what the need would be to use another one, but direct comparison between our code and another one is not so much in our interest, right? So.
Yeah, but that followed up with the discussion when you said that one can, in principle, put the 4F electrons if they localize in the core. So there could be some kind of tunability in designing the pseudopotential could be helpful. Or can we actually?
Yes. Oh, yeah. Okay. Well, that is one thing which I should probably explicitly mention. So there are pseudopotentials where that stuff has been put into the core. Those are available. If you have particular needs, then I really suggest you rely on Georg Kresse to construct a potential. We don't distribute the software to construct the potentials with, not because we think that we don't think it's wise actually. I mean, construction of pseudo potentials unless you really know what you're doing, it is where sort of the magic happens. This is still a sort of alchemy. You turn a bit here, you turn a bit here, and it's a huge parameter space. And people's brains, connected with experience, can find a way through this parameter space. If you don't know what you're doing, it's very, very easy to make a bad potential. So we don't actually encourage this at all. I would not try my hand at it, and I'm already in this field for a very long time. If I need something, I go to one room and say, please, can you make this ghost state disappear? Yeah, and it is. So tinkering with it would lead to many problems. Is my impression.
So a few, I guess, operational questions.
Okay.
Earlier this morning you were talking about aliasing errors. So if I've performed a calculation, how can I tell either afterwards or before the fact whether or not that calculation has aliasing problems?
Right. So, well, first of all, VASP will tell you this, whether there's aliasing present in the current choice of grids. If, however, you choose your grids if the grids are chosen such that the grid, which is commonly called, there's unfortunately nothing to write on.
You can write on the wall.
Really?
Yeah, that's
Whoa. If my mother would see this. Yeah, so there's a quantity that is called ngx or y or z. And there's one, and it's in the outcore file. And there's one that is called ngxf, yf, yz. So if this one is 2 times this one, then the grid used to represent the charge density should be free of aliasing. Well, it should be at least 2 times that one. Right. So that would be. But if you set this, precision is A or precision is accurate. You would only sensitive to the first character. If you set precision to accurate, you're guaranteed to be free of aliasing in the representation of the charge density. Yeah.
okay. I think it's lunchtime. We can defer some online questions later. Yeah.
Okay. Cool.